Welcome. Our lecture today is on quantum computing in theory, dismantling RSA encryption with Shor's algorithm, a groundbreaking development in quantum computing that fundamentally challenges our current approach to encryption security. In 1994, Peter Shor introduced an algorithm that would later become one of the most compelling arguments for the development of quantum computers. To understand its significance, imagine trying to break open a safe that would take longer than the age of the universe to crack using traditional methods. Shor's algorithm transforms this impossible task into one that takes mere minutes. The algorithm's power lies in its ability to efficiently factor large numbers, a task that forms the backbone of many modern encryption systems. While we often demonstrate this using small numbers for educational purposes, the real impact comes at scale. A quantum computer with several thousand qubits could potentially decrypt messages that would be practically impossible to crack using classical computing methods. This capability has created a fascinating situation in the cybersecurity landscape. Rather than waiting for quantum computers to become powerful enough to implement Shor's algorithm at scale, organizations worldwide are already developing what we call post-quantum cryptography. These are new encryption methods specifically designed to resist both classical and quantum attacks. The implementation of Shor's algorithm involves sophisticated mathematical concepts, including complex numbers and period-finding functions. Today, we can explore these concepts using quantum computing frameworks like Qiskit, which allows us to experiment with the algorithm's principles on a smaller scale. Consider this question. If Shor's algorithm makes our current encryption methods vulnerable, why don't we immediately switch to post-quantum cryptography? What are the technical and practical considerations that influence this decision? To address this question, we need to consider several factors. First, while Shor's algorithm poses a theoretical threat, we don't yet have quantum computers powerful enough to implement it at a scale that could break real-world encryption. Second, post-quantum cryptography systems are still under development and need thorough testing to ensure they're both secure and practical. Finally, transitioning global infrastructure to new encryption standards is a massive undertaking that requires careful planning and coordination. Understanding these challenges helps us appreciate why this is such an active area of research and development. As we move forward in our study of quantum algorithms, we'll see how these fundamental concepts connect to broader applications in quantum computing and cryptography. Now we're exploring one of the most elegant concepts in modern cryptography, RSA encryption. This remarkable system, introduced in 1977 by Rives, Shamir, and Adelman, demonstrates how a simple mathematical principle can create nearly unbreakable security. Let's examine the brilliant mathematical insight at the heart of RSA. Looking at our figure, we see two 50-digit numbers being multiplied together. The first number is 3797422793694373920888727 and the second is 40094011 When multiplied, they produce a 100-digit number. Modern computers can perform this multiplication almost instantaneously. However, the true genius of RSA lies in what happens when we try to reverse this process. If I give you just the resulting 100-digit number, something and ask you to find its two 50-digit factors. Even powerful computers struggle. In fact, when this problem was submitted to a sophisticated mathematics platform, it exceeded the system's computational limits. This asymmetry, the fact that multiplication is computationally simple, while factorization is computationally difficult, forms the cornerstone of RSA encryption's security. It's what cryptographers call a one-way function, easy to compute in one direction, but extremely difficult to reverse. Here's a thought-provoking question to consider. Why do you think the creators of RSA chose specifically to work with 50-digit numbers in this example? How would the security implications change if we used significantly smaller or larger numbers? To explore this question, let's consider the mathematical relationships at play. With small numbers, say two-digit numbers, both multiplication and factorization are trivial tasks for computers. As we increase the number of digits, multiplication remains relatively simple. It scales linearly with the size of the numbers. However, the difficulty of factorization grows exponentially. At 50 digits, we've reached a sweet spot where multiplication remains practical, while factorization becomes virtually impossible with classical computing methods. This mathematical property creates a perfect security mechanism. Anyone can easily encrypt a message using multiplication, but decrypting it without the proper keys would require solving an essentially impossible factorization problem. This insight revolutionized the field of cryptography and continues to protect countless secure communications today. As we move forward in our exploration of encryption systems, we'll see how this fundamental principle of computational asymmetry appears in various forms throughout modern cryptography, and why it's so crucial for securing our digital world. RSA encryption, a brilliant system that revolutionized secure communication by introducing the concept of public key cryptography. Let's analyze how this system works using a practical scenario involving three parties: Alice, Bob, and an eavesdropper named Eve. Looking at our diagram, we see Alice starting the process by generating her private key, which consists of two very large 1024-bit numbers. Think of these as her secret combination to unlock encrypted messages. She then performs a simple multiplication of these numbers to create a 248-bit public key. This public key can be freely shared with anyone, even potential eavesdroppers like Eve. The beauty of this system becomes apparent when we follow Bob's actions. Bob wants to send a secure message to Alice. He takes Alice's public key, the 248-bit number, and uses it to encrypt his message. The result is what appears to be gibberish, represented in our diagram as n%, 9, 12, bar. Now, let's observe Eve's attempts to intercept this communication. The diagram shows Eve's thought process through two speech bubbles. In the first, she acknowledges that while she has access to the 2048-bit public key, merely having this number doesn't help her encrypt her own message. That's not her goal. In the second bubble, she expresses frustration because even though she has intercepted Bob's encrypted message, she can't decrypt it without Alice's private key numbers. The task of factoring the 2048-bit public key to find these numbers would take an impossibly long time on classical computers. Here's a thought-provoking question to consider. Why is it significant that RSA encryption uses such specific bit lengths, 10 to 24 bits for the private key numbers and 2048 bits for the public key? How do these numbers relate to the security efficiency trade-off in cryptography? To explore this question, we need to understand the delicate balance at play. The 1024-bit length for each private key number is carefully chosen to be large enough that factoring their product, the 2048-bit public key, is computationally infeasible with current technology. However, these numbers are also small enough that the multiplication to create the public key and the encryption Shor decryption processes can still be performed efficiently. The system's security relies on this asymmetry. Multiplication of large numbers is computationally simple, while factoring their product is extraordinarily difficult. This fundamental principle allows RSA to achieve what seems paradoxical: a secure encryption system where the key for encrypting messages can be made completely public. This leads us naturally into understanding why RSA is called an asymmetric encryption system. Unlike traditional encryption methods, where the same key is used for both encryption and decryption, RSA uses different keys for these operations, with one being public and the other private. This asymmetry is what makes RSA particularly valuable for secure communication in our digital world. The token function and its relationship with coprime numbers. Let's break this down step by step using a concrete example from our equation. Looking at our figure, we see the calculation. Token 5, 1, 11, 1 in 40. This seemingly simple equation actually represents a fundamental concept in cryptography. The token function, when working with two prime numbers, is calculated by subtracting 1 from each prime number and then multiplying these results together. Why is this calculation important? The token gives us a crucial value that helps establish the mathematical foundation for secure encryption. In our example, using the prime numbers 5 and 11, we subtract 1 from each to get 4 and 10, then multiply these together to obtain 40 as our token. Once we have our token value of 40, we need to select what's called a coprime number. This selection process is governed by two strict rules. First, the number must be less than our token of 40. Second, and more importantly, it must have no common divisors with 40, except for 1. Let's analyze why certain numbers wouldn't work as coprimes. Take the number 5. It can't be used because it divides evenly into our token of 40. Similarly, 6 isn't suitable because it shares a common divisor, 2, with 40. However, 7 works perfectly as a coprime because its only divisors are 1 and 7, neither of which divide evenly into 40, except for 1, which is allowed. Here's a thought-provoking question to consider. How does the choice of initial prime numbers, in this case 5 and 11, affect the range of possible coprime numbers available for selection? What implications might this have for the security of the encryption system? To explore this question, let's think about the relationships involved. When we choose our initial prime numbers, we're not just selecting two random numbers. We're setting up a chain of mathematical consequences. The prime numbers determine our token, which in turn determines our pool of possible coprime numbers. The larger our initial prime numbers, the larger our token becomes, which gives us a wider range of potential coprime numbers to choose from. This relationship is crucial because having more coprime options makes the encryption system more secure. In our example with a token of 40, we have a relatively small pool of possible coprimes. But in real-world applications, where much larger prime numbers are used, the number of possible coprimes becomes astronomically large, making it much harder for anyone to guess which coprime was selected. This concept of carefully chosen numbers working together, the prime numbers, their token, and a selected coprime, forms one of the fundamental building blocks of RSA encryption's security. Understanding these relationships helps us appreciate why RSA remains such a robust encryption method when implemented with sufficiently large numbers. On the inverse coprim, let's examine the equation before us. Coprim inverse a coprime, percent totient equal 1. This elegant mathematical expression encapsulates a crucial relationship in RSA encryption. The percent sign here represents the modulo operation, which gives us the remainder after division. What we're looking for is a number, the inverse coprime, that when multiplied by our original coprime and divided by the totient leaves a remainder of 1. Think of the inverse coprime as a mathematical complement to our original coprime. If the coprime is like a key that locks the message, the inverse coprime is the corresponding key that unlocks it. Their relationship through the modulo operation with the totient creates a perfect mathematical balance that makes secure encryption and decryption possible. Let's break this equation down step by step. We start with our coprime number, which we previously established must share no common factors with the totient. We multiply this by another number, our inverse coprim. When we divide this product by the totient, the remainder must be exactly 1. This property is crucial because it ensures that our encryption process is reversible, that we can decrypt what we've encrypted. The beauty of this relationship is that while it's relatively straightforward to calculate the inverse coprime when you know the totient and coprime, it's computationally intensive to figure out without this information. Here's a thought-provoking question to consider. Why is it significant that the modulo operation with the totient must yield exactly 1? How would the encryption system behave if we allowed other remainders? And why might this make the system less secure or even non-functional? To explore this question, let's think about the mathematical implications. The requirement for a remainder of 1 isn't arbitrary. It ensures a unique and reversible relationship between our coprime and inverse coprime. If we allowed other remainders, we might create ambiguity in the decryption process. The value of 1 represents a special mathematical property that guarantees our ability to recover the original message. This relationship between coprime, inverse coprime, and totient creates what mathematicians call a modular multiplicative inverse. It's one of the fundamental building blocks that makes RSA encryption both secure and reliable. The fact that this relationship must exist and must yield a remainder of 1 is what allows us to decrypt messages with mathematical certainty while still maintaining the security of our encryption system. Understanding this concept helps us appreciate the elegant mathematical foundation of RSA encryption. The inverse coprime isn't just another number in the system. It's a carefully chosen value that satisfies a precise mathematical requirement, ensuring our encryption system is both secure and reversible. Now we're examining a concrete example of modular arithmetic that demonstrates how we find and verify an inverse coprime in RSA encryption. Let's analyze the equation before us. 7, 23% 40 equal 161% 41. This equation shows us the verification process for an inverse coprime in action. We're working with 3 important numbers: our original coprime 7, our candidate inverse coprime 23, and our totient 40. Let's walk through this step by step to understand exactly what's happening. First, we multiply our coprime 7 by our candidate inverse coprime 23, which gives us 161. Then comes the crucial step. We apply the modulo operation, represented by the percent symbol, with our totient 40. When we divide 161 by 40, we get a remainder of 1. This is exactly what we're looking for. This remainder of 1 confirms that 23 is indeed a valid inverse coprime for our original coprime 7 under modulo 40. The beauty of this calculation lies in its simplicity and its importance. While the numbers we're using here are small for demonstration purposes, the same principle applies when working with the massive numbers used in real-world RSA encryption. Here's a thought-provoking question to consider. In this example, how many other possible numbers besides 23 could serve as the inverse coprime for 7 modulo 40? What pattern might these alternative solutions follow, and why does it matter for RSA encryption? To explore this question, we need to think about the nature of modular arithmetic. When working modulo 40, numbers that differ by multiples of 40 will give us the same remainder. This means that while 23 works as our inverse coprime, there might be other numbers that would also work. However, we typically choose the smallest positive number that satisfies our equation. This understanding is crucial because it shows us that even in this simple example with small numbers, there's an underlying pattern to how these numbers relate to each other. When we scale this up to the large numbers used in real RSA encryption, these patterns become even more important. The relationship between our coprime, its inverse, and the token creates a mathematical foundation that ensures our encryption system is both secure and reversible. The fact that we can verify this relationship with a simple calculation, multiplication followed by a modulo operation, while finding the inverse coprime itself is a more complex process, is part of what makes RSA encryption so effective. It's much easier to verify that we have the right answer than it is to find that answer in the first place, a principle that lies at the heart of many cryptographic systems. Today, we're examining a complete example of RSA encryption components working together. Let's analyze this table that presents all the essential elements of the RSA system in one clear view. Starting at the top of our table, we see the private key consisting of two prime numbers, 5 and 11. These numbers are the foundation of our encryption system. When multiplied together, they create our public key of 55. This relationship between private and public keys demonstrates the elegant simplicity of RSA's basic principle. Multiplication is computationally simple, while factoring is computationally difficult. Moving down the table, we see the token value of 40, which we calculated earlier using the formula 5 to 1, 11 to 1. This token plays a crucial role in determining our next two values, the coprime 7 and its inverse coprime 23. Remember, these numbers satisfy our modular arithmetic requirement where 7 23%, 41. What's particularly interesting is how these components are used in practice. Alice shares two specific pieces of information publicly, the public key 55 and the coprime 7. These numbers will allow Bob to encrypt his message, in this case, the number 9. The meaning of this number could be anything from a simple ASCII code to a coded military command. But the beauty of RSA is that it works regardless of what the numbers represent to the communicating parties. Here's a thought-provoking question to consider. Looking at this complete set of RSA values, why do you think Alice shares both the public key and the coprime with Bob? Couldn't an attacker use this additional information to try to break the encryption? How does sharing both numbers actually enhance the security of the system rather than compromise it? To explore this question, we need to understand the interplay between these components. The public key and coprime work together as part of the encryption formula, but knowing both numbers still doesn't help an attacker reverse the process. This is because the security relies on the computational difficulty of factoring the public key, 55, into its prime components, 5 and 11, not on keeping the encryption process itself secret. The inverse coprime, 23, remains private, known only to Alice, and this is what makes the system secure. Even with both the public key and coprime, an attacker would need to factor 55 to calculate the token and subsequently find the inverse coprime. With the small numbers in our example, this would be trivial, but with the large numbers used in real RSA encryption, it becomes computationally infeasible. This table thus represents a perfect microcosm of how RSA encryption balances openness and security. It shows us exactly which numbers can be shared publicly and which must be kept private, illustrating the fundamental principle of public key cryptography, that we can create a secure system even when much of its operational information is publicly available. The mathematical formula that transforms our plain text message into encrypted ciphertext. Let's analyze the elegant equation before us and its practical application. The formula we're looking at is plain text coprime percent public key equals ciphertext. In our specific example, this becomes 97% 50 equals 4. This seemingly simple equation encapsulates the entire encryption process in one powerful operation. Let's break down exactly what's happening here. We start with our plain text message, the number 9. This gets raised to the power of our coprime, which is 7. Then we perform a modulo operation using our public key, 55 key, which gives us our final ciphertext of 4. This transformed number 4 is what Bob would actually send to Alice. What's fascinating about this process is how it uses modular arithmetic to create a one-way function. Even though everyone can see the formula and the numbers being used, the mathematics ensures that without the private key, it's computationally infeasible to reverse the process and recover the original plain text. Here's a thought-provoking question to consider. Why do we raise the plain text to the power of the coprime before applying the modulo operation? How would the security of the system be affected if we simply use multiplication instead of exponentiation? To explore this question, let's think about the mathematical properties at work. The use of exponentiation creates a much more complex mathematical relationship than simple multiplication would. When we raise 9 to the 7th power, we get a very large number that then gets reduced, modulo 55. This process creates a kind of mathematical mixing that is much harder to reverse than if we had just multiplied the numbers. The beauty of this formula lies in its asymmetry. It's relatively straightforward to compute in one direction, encryption, but extremely difficult to reverse a decryption without the proper keys. In our example, computing 97% 55 equals 4 is a straightforward calculation, but trying to determine that 4 came from an original value of 9 without knowing the private key factors would be a much more challenging task. Even with these small numbers, we can see how the formula creates a secure transformation of our message. When we scale this up to the large numbers used in real-world RSA encryption, with hundreds or thousands of digits, this simple formula becomes an incredibly powerful tool for secure communication. The mathematical principles remain exactly the same. We're just working with much larger numbers that make the encryption even more secure. The decryption process. Let's examine how Alice recovers the original message using her secret inverse coprime. The decryption formula mirrors the encryption formula in its elegance. Ciphertext inverse coprime percent public key gish plain text. In our specific example, this becomes 423% 55 equals 9. This formula reveals how Alice can recover Bob's original message of 9 from the encrypted value of 4. What's particularly fascinating about this process is that Alice never directly uses her private key numbers, 5 and 11, in the decryption calculation itself. Instead, she uses the inverse coprime of 23, which she previously derived using those private numbers. This adds an extra layer of security to the system. Even if someone were to intercept the decryption process, they wouldn't directly see the private key numbers. Let's analyze why this works mathematically. When we raise the ciphertext 4 to the power of the inverse coprime 23 and take the modulo with respect to the public key 55, we get back our original plain text message 9. This isn't a coincidence. It's a result of the careful mathematical relationships we established earlier between the coprime, inverse coprime, and token. Here's a thought-provoking question to consider. Why is it significant that the private key numbers aren't directly used in the decryption process? How does this indirect use of the private key through the inverse coprime enhance the security of the RSA system? To explore this question, let's think about the layers of security this creates. The private key numbers, 5 and 11, are used to generate the token 40, which in turn is used to find the inverse coprime 23. This multi-step derivation means that even if an attacker somehow captured a snapshot of the decryption process in action, they would only see the inverse coprime being used, not the original private key numbers. This is a brilliant security feature because it means the most fundamental secrets of the system, the private key numbers, are never exposed during actual encryption or decryption operations. They're only used during the initial setup phase to derive the inverse coprime. Once that's done, they can be stored securely away from any active operations. This design principle exemplifies a key concept in cryptography: the separation of key generation from key use. The private key numbers are used to generate the decryption parameters, but aren't needed for the actual decryption process. This separation helps protect the most sensitive parts of the system while still allowing for efficient message decryption. Understanding this aspect of RSA helps us appreciate the elegant balance between security and usability in the system. The mathematics allows us to keep our most sensitive numbers, the private key, completely separate from the actual encryption and decryption operations, while still maintaining the ability to securely communicate. Now we're exploring a fundamental concept in Shor's algorithm: how finding patterns in number sequences can unlock the secrets of encryption. Let's examine this fascinating mathematical process step by step. Imagine Eve, our hypothetical code breaker, intercepting a public key of 15. Instead of trying to factor 15 directly, she takes an ingenious approach using pattern recognition. She starts by choosing a coprime number, in this case 2, and begins generating a sequence through a specific mathematical operation. Looking at our figure, we can see exactly how this sequence develops. Eve starts with 2 modulo 15, which gives us 1. Then 2 1 modulo 15 gives us 2. As she continues this process, raising 2 to increasingly higher powers, and taking the remainder when divided by 15, a clear pattern emerges: 1, 2, 4, 8, 1, 2, 4, 8, and so on. What's particularly fascinating is how this sequence, which we call a coprime power sequence, repeats every 4 numbers. Let's track the calculations. 2 results 1, 2, 1, 2, 2, 2 as 4, 2, 3, 8, 2, 4, 16, which gives us 1 when divided by 15. And the pattern continues, cycling through these same 4 values. Here's a thought-provoking question to consider. Why might the length of this repeating sequence, in this case, 4 numbers, be significant? How might the period length of such a sequence relate to the factors of our public key 15? To explore this question, let's think about what creates this repetition. The fact that we keep getting the same sequence of remainders tells us something profound about the mathematical structure of our public key 15. The length of this repetition isn't random. It's intimately connected to the hidden factors we're trying to find. This is where Shor's algorithm shows its brilliance. Instead of trying to factor the number directly, it looks for these cyclical patterns. The length of these cycles, combined with some sophisticated quantum computing techniques, can reveal the factors of our public key. Even in this simple example with 15, we can see how the regular pattern of 1, 2, 4, 8 might help us unlock its structure. What makes this approach particularly clever is that it transforms the difficult problem of factoring into a different kind of problem: finding periods in sequences. While this might not seem like a huge advantage with small numbers like 15, when we scale up to the massive numbers used in real encryption, this transformation becomes incredibly powerful, especially when implemented on a quantum computer. Understanding this pattern-finding approach helps us appreciate why Shor's algorithm represents such a fundamental threat to current encryption methods. It doesn't attack the factoring problem head-on. Instead, it finds a clever mathematical backdoor through pattern recognition. Now we're examining the crucial final step in Shor's algorithm: how we transform our discovery of a period into the actual factors of our public key. This is where the mathematical elegance of the algorithm truly shines. Let's analyze the equations before us. After discovering that our sequence has a period of 4, Eve performs two critical calculations. First, she computes coprime period up to 1, which in our case is 2, 4, 2, 1, or 2, 2, 1, giving us 3. Then she computes coprime period 2 plus 1, which is 2 plus 2 plus 1, giving us 5. This isn't just arbitrary arithmetic. These calculations reveal the hidden factors of our public key, 15. Indeed, 3 and 5 are precisely the prime numbers we've been searching for. What makes this particularly remarkable is how we arrived at these factors, not through brute force division attempts, but through analyzing patterns in a sequence. Let's understand why these particular calculations work. When we raise our coprime 2 to half the period, 4, 2, 6, 2, we're leveraging a special mathematical property. The addition and subtraction of 1 from this result splits our public key perfectly along its prime factorization. Here's a thought-provoking question to consider. Why does raising the coprime to exactly half the period work so effectively? What mathematical properties make this specific power, period talk 2, so special in revealing the factors of our public key? To explore this question, let's think about what the period represents. The period of 4 tells us how long it takes for our sequence to repeat when we're taking modulo 15. This repetition period isn't arbitrary. It's intimately connected to the multiplicative properties of the numbers involved. When we use half of this period as our exponent, we're essentially finding a mathematical sweet spot that exposes the underlying structure of our public key. The beauty of this method is that it transforms what seems like a simple pattern finding exercise into a powerful factorization tool. By discovering that the sequence repeats every 4 numbers, we've uncovered enough information to split 15 into its prime factors of 3 and 5. This means Eve has successfully broken the encryption. She now knows Alice's private key numbers. This final step demonstrates why Shor's algorithm is so revolutionary. Instead of testing countless possible factors, it uses the quantum properties of period finding to lead us directly to the factors through these elegant calculations. While our example uses the small number 15, the same principles apply to the massive numbers used in real-world encryption, which is precisely why quantum computers pose such a significant threat to current cryptographic systems. The decryption process. Let's examine how Alice recovers the original message using her secret inverse coprime. The decryption formula mirrors the encryption formula in its elegance. Ciphertext inverse coprime. Percent. Public key gauge plain text. In our specific example, this becomes 423%, 55 equals 9. This formula reveals how Alice can recover Bob's original message of 9 from the encrypted value of 4. What's particularly fascinating about this process is that Alice never directly uses her private key numbers, 5 and 11, in the decryption calculation itself. Instead, she uses the inverse coprime of 23, which she previously derived using those private numbers. This adds an extra layer of security to the system. Even if someone were to intercept the decryption process, they wouldn't directly see the private key numbers. Let's analyze why this works mathematically. When we raise the ciphertext 4 to the power of the inverse coprime 23 and take the modulo with respect to the public key 55, we get back our original plain text message 9. This isn't a coincidence. It's a result of the careful mathematical relationships we established earlier between the coprime, inverse coprime, and tochin. Here's a thought-provoking question to consider. Why is it significant that the private key numbers aren't directly used in the decryption process? How does this indirect use of the private key through the inverse coprime enhance the security of the RSA system? To explore this question, let's think about the layers of security this creates. The private key numbers, 5 and 11, are used to generate the tochin 40, which in turn is used to find the inverse coprime 23. This multi-step derivation means that even if an attacker somehow captured a snapshot of the decryption process in action, they would only see the inverse coprime being used, not the original private key numbers. This is a brilliant security feature because it means the most fundamental secrets of the system, the private key numbers, are never exposed during actual encryption or decryption operations. They're only used during the initial setup phase to derive the inverse coprime. Once that's done, they can be stored securely away from any active operations. This design principle exemplifies a key concept in cryptography: the separation of key generation from key use. The private key numbers are used to generate the decryption parameters, but aren't needed for the actual decryption process. This separation helps protect the most sensitive parts of the system while still allowing for efficient message decryption. Understanding this aspect of RSA helps us appreciate the elegant balance between security and usability in the system. The mathematics allows us to keep our most sensitive numbers, the private key, completely separate from the actual encryption and decryption operations, while still maintaining the ability to securely communicate. Now we're exploring a fundamental concept in Shor's algorithm: how finding patterns in number sequences can unlock the secrets of encryption. Let's examine this fascinating mathematical process step by step. Imagine Eve, our hypothetical code breaker, intercepting a public key of 15. Instead of trying to factor 15 directly, she takes an ingenious approach using pattern recognition. She starts by choosing a coprime number, in this case 2, and begins generating a sequence through a specific mathematical operation. Looking at our figure, we can see exactly how this sequence develops. Eve starts with 2 modulo 15, which gives us 1. Then 2 1 modulo 15 gives us 2. As she continues this process, raising 2 to increasingly higher powers, and taking the remainder when divided by 15, a clear pattern emerges: 1, 2, 4, 8, 1, 2, 4, 8, and so on. What's particularly fascinating is how this sequence, which we call a coprime power sequence, repeats every 4 numbers. Let's track the calculations. 2 results 1, 2, 1 equal 2, 2, 2 as 4, 2, 3, 8, 2, 4, 16, which gives us 1 when divided by 15. And the pattern continues, cycling through these same 4 values. Here's a thought-provoking question to consider. Why might the length of this repeating sequence, in this case, 4 numbers, be significant? How might the period length of such a sequence relate to the factors of our public key 15? To explore this question, let's think about what creates this repetition. The fact that we keep getting the same sequence of remainders tells us something profound about the mathematical structure of our public key 15. The length of this repetition isn't random. It's intimately connected to the hidden factors we're trying to find. This is where Shor's algorithm shows its brilliance. Instead of trying to factor the number directly, it looks for these cyclical patterns. The length of these cycles, combined with some sophisticated quantum computing techniques, can reveal the factors of our public key. Even in this simple example with 15, we can see how the regular pattern of 1, 2, 4, 8 might help us unlock its structure. What makes this approach particularly clever is that it transforms the difficult problem of factoring into a different kind of problem: finding periods in sequences. While this might not seem like a huge advantage with small numbers like 15, when we scale up to the massive numbers used in real encryption, this transformation becomes incredibly powerful, especially when implemented on a quantum computer. Understanding this pattern-finding approach helps us appreciate why Shor's algorithm represents such a fundamental threat to current encryption methods. It doesn't attack the factoring problem head-on. Instead, it finds a clever mathematical backdoor through pattern recognition. Now we're examining the crucial final step in Shor's algorithm: how we transform our discovery of a period into the actual factors of our public key. This is where the mathematical elegance of the algorithm truly shines. Let's analyze the equations before us. After discovering that our sequence has a period of 4, Eve performs two critical calculations. First, she computes coprime period up to 1, which in our case is 2, 4, 2, 1, or 2, 2, 1, giving us 3. Then she computes coprime period 2 plus 1, which is 2 is 2 plus 1, giving us 5. This isn't just arbitrary arithmetic. These calculations reveal the hidden factors of our public key, 15. Indeed, 3 and 5 are precisely the prime numbers we've been searching for. What makes this particularly remarkable is how we arrived at these factors, not through brute force division attempts, but through analyzing patterns in a sequence. Let's understand why these particular calculations work. When we raise our coprime 2 to half the period, 4262, we're leveraging a special mathematical property. The addition and subtraction of 1 from this result splits our public key perfectly along its prime factorization. Here's a thought-provoking question to consider. Why does raising the coprime to exactly half the period work so effectively? What mathematical properties make this specific power, period top 2, so special in revealing the factors of our public key? To explore this question, let's think about what the period represents. The period of 4 tells us how long it takes for our sequence to repeat when we're taking modulo 15. This repetition period isn't arbitrary. It's intimately connected to the multiplicative properties of the numbers involved. When we use half of this period as our exponent, we're essentially finding a mathematical sweet spot that exposes the underlying structure of our public key. The beauty of this method is that it transforms what seems like a simple pattern finding exercise into a powerful factorization tool. By discovering that the sequence repeats every 4 numbers, we've uncovered enough information to split 15 into its prime factors of 3 and 5. This means Eve has successfully broken the encryption. She now knows Alice's private key numbers. This final step demonstrates why Shor's algorithm is so revolutionary. Instead of testing countless possible factors, it uses the quantum properties of period finding to lead us directly to the factors through these elegant calculations. While our example uses the small number 15, the same principles apply to the massive numbers used in real-world encryption, which is precisely why quantum computers pose such a significant threat to current cryptographic systems. Awesome. Now we're exploring a fascinating variation in Shor's algorithm by examining what happens when we choose a different coprime number. In our previous example, we used 2 as our coprime. Now, let's analyze in detail what happens when we use 7 as our coprime against the same public key of 15. Let's break down the mathematical sequence step by step, examining each calculation in precise detail. Starting with 7 and 0 modulo 15, we get 1. This is because any number raised to the power of 0 equals 1, and 1 modulo 15 is simply 1. Moving to 7 or 1 modulo 15, we get 7. This is straightforward as 7 is less than 15, so the modulo operation simply returns 7. For 7 2 modulo 15, we calculate 49, which when divided by 15 gives us a remainder of 4. This calculation shows us how the modulo operation keeps our numbers manageable while preserving the mathematical properties we're interested in. At 7 and 3 modulo 15, we're dealing with 343, which gives us a remainder of 13 when divided by 15. Notice how, even though our raw numbers are getting quite large, 343, the modulo operation keeps bringing us back to a manageable number between 1 and 14. When we reach 7 4 modulo 15, we are calculating the remainder of 2401 divided by 15, which brings us back to 1. This is our first indication of a pattern, as we've returned to our starting value. Continuing the sequence, 7 5 modulo 15 gives us 7 again from 16807. 7,006 modulo 15 returns 4 from 117649, and 7 7 modulo 15 produces 13 from 8 23543. Finally, 7 or 8 modulo 15 brings us back to 1 from 5764801. What's particularly fascinating is that we've discovered another sequence with a period of 4, 1, 7, 4, 13, which repeats indefinitely. While these specific numbers are different from our previous sequence using coprime 2, which gave us 1, 2, 4, 8, the period length remains the same. Here's a thought-provoking question to consider. How does the choice of coprime affect the values in the sequence while maintaining the same period length? What mathematical principle ensures that different coprimes against the same public key produce sequences with equal periods but different values? To explore this question, let's analyze the deeper mathematical structure at work. The fact that both coprime 2 and coprime 7 produce sequences with period 4, despite generating different values, reveals something fundamental about the multiplicative structure of 15. This consistency in period length, regardless of our choice of coprime, is not coincidental. It's a direct result of the prime factorization of 15 into 3 and 5. The calculations show that even as our base numbers grow exponentially, 1, 7, 49, 343, 2401, 16807, 11, 649, 823, 543, 576, 4801, the modulo operation with 15 constrains our results to a repeating pattern of just 4 numbers. This demonstrates the power of modular arithmetic in creating manageable, periodic sequences from potentially enormous numbers. This property is crucial for Shor's algorithm because it means we can reliably find patterns regardless of which valid coprime we choose. The period length itself, rather than the specific values in the sequence, is what ultimately leads us to the factors of our public key. This robustness that different coprimes produce different sequences but preserve the crucial period length is part of what makes Shor's algorithm so powerful and reliable. Next, we're examining a fascinating alternative path to factorization in Shor's algorithm, demonstrating how different coprimes can lead us to the same fundamental truth. Let's analyze this remarkable mathematical process in precise detail. When Eve uses 7 as her coprime instead of 2, she discovers something remarkable. The sequence still has a period of 4. This is particularly interesting because while this equality of periods isn't guaranteed for all cases, it provides us with a powerful tool for factorization. Let's break down the calculations with extreme precision. Using the period of 4, Eve computes 2 critical values. First, she calculates coprime period 2, 1, which is 7 over 2, 1, 1 equals 48. When we examine 48's prime factorization, we get 2 by 2 by 2 by 2 by 3. This is our first hint at one of the factors we're seeking. The number 3 appears in this factorization. Then she computes coprime period 2 plus 1, which is 7 and 2 plus 1 = 50. The prime factorization of 50 gives us 2555. Here we find our second crucial factor, the number 5. What makes this particularly fascinating is that we now have 3 numbers, 48, 50, and our public key 15, that contain within their structure the factors we're seeking. Through mathematical comparison of these numbers, Eve can deduce that 15 must be the product of 3 and 5. Let's examine why this works in excruciating detail. The fact that 48 contains a factor of 3 and 50 contains a factor of 5 is not coincidental. These numbers derive from raising our coprime to half the period and then adding or subtracting 1, somehow magically split our public key into its constituent prime factors. Next, we're examining a fascinating alternative path to factorization in Shor's algorithm, demonstrating how different coprimes can lead us to the same fundamental truth. Let's analyze this remarkable mathematical process in precise detail. When Eve uses 7 as her coprime instead of 2, she discovers something remarkable. The sequence still has a period of 4. This is particularly interesting because while this equality of periods isn't guaranteed for all cases, it provides us with a powerful tool for factorization. Let's break down the calculations with extreme precision. Using the period of 4, Eve computes 2 critical values. First, she calculates coprime period 2, 1, which is 7, 2, 1, 1 equals 48. When we examine 48's prime factorization, we get 2 bar 2 its 3. This is our first hint at one of the factors we're seeking. The number 3 appears in this factorization. Then she computes coprime period 2 plus 1, which is 7 and 2 plus 1 equals 50. The prime factorization of 50 gives us 2 by 5, 5. Here we find our second crucial factor, the number 5. What makes this particularly fascinating is that we now have 3 numbers, 48, Shor, 50, and our public key 15, that contain within their structure the factors we're seeking. Through mathematical comparison of these numbers, Eve can deduce that 15 must be the product of 3 and 5. Let's examine why this works in excruciating detail. The fact that 48 contains a factor of 3 and 50 contains a factor of 5 is not coincidental. These numbers derive from raising our coprime to half the period and then adding or subtracting 1. Somehow magically split our public key into its constituent prime factors. We're diving deep into one of the most fascinating aspects of Shor's algorithm, how the period of a sequence directly leads us to factoring numbers. We'll examine a specific example that beautifully demonstrates this connection through careful algebraic manipulation and logical deduction. Let's begin by analyzing the remarkable equation before us. We start with 2 terms that we previously calculated, 7, 4, 2, 1, and 7, 4, 2 plus 1. When we multiply these together, we perform an algebraic expansion that reveals something profound about the relationship between periods and factorization. The expansion proceeds as follows. First, we multiply 7, 4, 2, 1, 7, 4, 2 plus 1. This is a difference of squares pattern, which expands to 7, 4, 2 at 7, 4, 2. 7, 4, 2 is 7, 4, 2, 1. Notice how the middle terms cancel out, leaving us with the elegantly simple expression 7, 4, 1. Now, this is where the magic of periods in modular arithmetic comes into play. From our previous work with the coprime power sequence, we discovered that 7, 4%, 15, 1. This seemingly simple fact carries enormous implications for our factorization attempt. Let's follow the logical chain with precise mathematical reasoning. We know that 704% 15 equals 1. This means that when we divide 704 by 15, we get a remainder of 1. Therefore, 704 15k plus 1 for some integer, k, subtracting 1 from both sides. 704, 1 15k. This proves that 15 divides evenly into 7, 4, 1. And since 7 to 4, 1 is exactly what we got from multiplying 7, 4, 2, 1, 7 and 4, 2, 2 plus 1, we've proven that 15 divides evenly into this product. Here's a thought-provoking question to consider. Why does the period of 4 in our sequence lead to a perfect square situation when we raise 7 to that power? How does this specific mathematical structure guarantee that we can factor our target number? And would this work for any period length? To explore this question, let's analyze the deeper mathematical structure at work. The period of 4 isn't just any number. It represents the cycle length in our modular arithmetic sequence. When we use half of this period, 4 2 equals 2, in our calculations, we're leveraging a fundamental property of modular arithmetic that connects periodic behavior to factorization. The fact that our expansion simplifies to 7, 4, 1 is crucial. This expression must be divisible by 15 because of the periodic property we discovered. But it's divisible by 15 in a very special way. It splits perfectly into factors that help us reveal the structure of 15 itself. Think about what's happening algebraically. We started with 2 numbers, 7,422, 1 and 74422 plus 1, that when multiplied together give us something divisible by 15. This isn't just any factorization. It's a factorization that preserves the prime structure of 15 in a way that we can recover. The elegance of this approach lies in how it transforms our original factoring problem. Instead of trying to factor 15 directly, we've used the period of our sequence to construct numbers that must contain the factors of 15 within their own structure. The period essentially gives us a mathematical lever to split our target number along its prime factorization. This connection between periodic behavior in modular arithmetic and prime factorization is what makes Shor's algorithm so powerful. We're not just finding any numbers that multiply to give us multiples of 15. We're finding specific numbers whose structure is intimately connected to the prime factors we're seeking. We're exploring a profound mathematical principle that lies at the heart of RSA encryption, the fundamental nature of prime numbers and their role in factorization. Let's analyze this fascinating expression that emerges from our previous calculations with Shor's algorithm. Before us is an expression that appears deceptively simple. 2 power 2 cook 3, 2 are 5, divided by 3 by 5. This fraction encapsulates a deep mathematical truth about the nature of prime numbers and their role in factorization. Let's dissect this expression with meticulous attention to detail. In the numerator's first term, we have 2 multiplied by itself 4 times, followed by 3. 2 with 3. This comes from our earlier calculation of 7 4 2 1, which equals 48. The second term in the numerator, 2 by 5, comes from 7 4 2 plus 1, which equals 50. In the denominator, we have the simple product 3 by 5, which is our target number 15. What makes this expression particularly fascinating is the appearance of the prime numbers 3 and 5 in both the numerator and denominator. This isn't a coincidence. It's a manifestation of a fundamental property of prime numbers. Let's understand why this must be the case. Consider the number 3 in the denominator. Since 3 is a prime number, it cannot be created by multiplying any 2 smaller integers together. As our lecture notes eloquently state, it's like an atomic particle of multiplication. It cannot be broken down any further. Therefore, if we're dividing by 3, that 3 must appear somewhere in the numerator to make the division possible. The same principle applies to the number 5. As another prime number, 5 is also mathematically atomic. It appears in our denominator as part of 15, 3 by 5. So it must necessarily appear in our numerator as well. Indeed, we find it appears twice in the term, 2 by 5, 5. Here's a thought-provoking question to consider. Why does this atomic nature of prime numbers make them so crucial for cryptography? How does the impossibility of breaking down prime numbers into smaller factors contribute to the security of RSA encryption? To explore this question, let's think about the mathematical structure we've uncovered. When we see prime numbers appearing in both numerator and denominator of our expression, we're witnessing a fundamental truth about factorization. Just as physical atoms combine to form molecules but cannot themselves be split through chemical means, prime numbers combine to form composite numbers but cannot be factored further. This property is what makes the factorization problem at the heart of RSA encryption so challenging. When we multiply 2 large prime numbers together to create our public key, we're essentially creating a mathematical molecule from 2 mathematical atoms. Finding those original prime factors is like trying to determine which specific atoms were used to create a molecule, a task that becomes increasingly difficult as the numbers get larger. The expression before us demonstrates this principle perfectly. The prime factors 3 and 5 appear in both numerator and denominator because they must. They are the fundamental building blocks of our original number 15. Their presence in the denominator forces their appearance in the numerator because you cannot create these prime numbers through any other combination of smaller numbers. This is why our expression maintains a perfect balance of prime factors. Every prime in the denominator must be accounted for in the numerator, just as every atom in a chemical equation must be accounted for on both sides. This isn't just a mathematical curiosity. It's a reflection of the fundamental nature of prime numbers and their role as the building blocks of all integers. Understanding this principle helps us appreciate why prime factorization is such a powerful tool in cryptography. The irreducible nature of prime numbers, their role as mathematical atoms, creates the mathematical foundation upon which secure communication can be built. We're exploring a fundamental principle in number theory that makes Shor's algorithm possible, the indivisible nature of prime numbers in factorization. Our visual aid perfectly illustrates this concept with a striking metaphor comparing prime numbers to atomic particles. Let's begin by examining the mathematical expression 742 742 plus 1 divided by 3 pi by 5. The crucial insight here is that when dealing with the prime factors 3 and 5, we cannot split them across different terms. They must appear whole, just as you cannot split an atom in purely mathematical operations. Looking at our diagram, we see two contrasting scenarios. On the left, marked with a clear NO, we have an invalid attempt to split the prime number 3 between the two terms. This is mathematically impossible. You cannot have part of 3 in 742 and another part in 742 plus 1. On the right side, marked yes, we see the correct approach. The prime factors must appear complete in either one term or the other. This principle leads us to a powerful method for finding factors. Since we know that 3 and 5 divide evenly into 742 plus 1, and we know they cannot be split, each prime factor must appear whole in either 742 or 742 plus 1. This gives us a practical way forward through the Euclidean algorithm. When Eve applies the Euclidean algorithm to find the greatest common divisor between 15 and 7422, she discovers that GCD 1548 in 3. This is a crucial breakthrough. Through simple division, she can then determine that 15 to 3 is 5, revealing both prime factors of the public key. Here's a thought-provoking question to consider. Why is the period finding aspect of Shor's algorithm so crucial, and how does the atomic nature of prime numbers make the algorithm's approach fundamentally different from brute force factorization attempts? To explore this question, we need to understand the interplay between period finding and prime factorization. The period, in our example 4, is the key that unlocks the factorization process. Without knowing this period, we couldn't construct the expression 742 plus 1, which gives us our crucial factors. The atomic nature of primes ensures that once we have this expression, the factors must appear whole in our calculations. They cannot be scattered or split across terms. This is where quantum computing enters the picture. While finding the period is computationally intensive for classical computers, potentially taking millennia for large numbers, quantum computers can perform this task efficiently using the quantum Fourier transform, QFT. The QFT provides a way to identify the period quickly, making the entire factorization process feasible. The beauty of this approach lies in its elegance. Instead of trying to factor numbers directly, we use period finding to create expressions that must contain whole prime factors. The indivisible nature of primes then guarantees that these factors must appear complete in our calculations, just as physical atoms remain whole in chemical reactions. For cryptographic purposes, this creates a fascinating situation. The security of RSA encryption relies on the difficulty of finding these periods using classical computers. However, with quantum computers capable of performing the QFT, the period finding problem becomes tractable, potentially compromising the encryption's security. This is why the development of quantum computers poses such a significant threat to current cryptographic systems, and why post-quantum cryptography is becoming increasingly important in the field of information security. We're exploring a powerful mathematical technique called repeated squaring, which transforms seemingly intractable calculations into manageable operations. Let's delve deep into how this method revolutionizes our ability to work with large numbers in modular arithmetic. Let's begin by examining the brute force approach, through our sequence of calculations with powers of 13 modulo 22. Following the direct calculation method, 13% 22 gives us 1, 13, 1% 22 equals 13, 13, 2% 22 requires calculating 169. Then finding the remainder, 15, 3% 22 involves calculating 2,197, yielding 19, 4% 22 means handling 28,561, resulting in 5, 13, 5% 22 requires calculating 371,293, giving us 21, 15, 6% 22 involves 4,826, 809, producing 9, 13, 7% 22 means dealing with 62,748,517, yielding 7, 13, 8%. 22 requires managing 815, 730, 721, resulting in 3. Notice how quickly these numbers grow. By the 8th power, we're dealing with a 9-digit number, and we haven't even reached a repeating pattern in our sequence. This growth becomes particularly problematic when we consider real-world applications using 2048-bit public keys. Enter the elegant solution of repeated squaring. The fundamental insight is that we can break down large exponential calculations into a series of smaller, more manageable ones by applying the modulo operation at each step. Let's examine how this works with our example of calculating 13.8% 22. Instead of calculating 1308 directly, we can think of it as 13.4.2. But we can go further. 13 to 4 itself can be calculated as 13 to 2. This gives us a systematic approach. First, calculate 13 to 2% 22 is 15. Then square that result, 15 2% 22 is 5. This gives us 13 4% 22. Finally, square again, 5 2% 22 in 3, giving us 13 8% 22. Here's a thought-provoking question to consider. How does the growth in computational complexity differ between direct calculation and repeated squaring when dealing with increasingly large exponents? What mathematical principle makes repeated squaring so much more efficient? To explore this question, let's analyze the computational efficiency. In the direct method, calculating 13.8 requires multiplying by 13.8 times, with each multiplication producing a larger number than the last. With repeated squaring, we only need 3 operations, finding 13 sur 2, then squaring twice, and our intermediate results never grow beyond 22, thanks to the modulo operation at each step. This efficiency becomes even more crucial when we scale up to cryptographic applications. Consider our example where we reduce calculating 815,730,721% 22 to simply computing 25% 22. This same principle applies to much larger numbers. Even when working with 2048-bit keys, repeated squaring keeps our intermediate calculations manageable. The beauty of repeated squaring lies in its logarithmic nature. While traditional multiplication requires operations proportional to the exponent, repeated squaring requires operations proportional to the logarithm of the exponent. This makes previously impossible calculations not just possible, but practical. This technique forms a crucial foundation for modern cryptography. Without repeated squaring, even basic operations in systems like RSA encryption would be computationally infeasible. The ability to efficiently perform modular exponentiation with large numbers is what makes secure communication possible in our digital world. We're examining the detailed implementation of repeated squaring in modular arithmetic, specifically how it revolutionizes our calculations of powers of 13 modulo 22. Let's break down this sophisticated process step by step. Let's begin with our fundamental calculations. The sequence starts with the trivial case of 13 0% 22 equal 1. Our first real calculation is 13 1% 22 equal 13, followed by 13 2% 22 equal 169% 22 equal 15. These base cases form the foundation for all our subsequent calculations. Now let's analyze how we build larger powers through clever combinations of smaller ones. For 13 3, Instead of multiplying 13 by itself 3 times, we use the factorization. 13 is 2, 13 or 1. In modular arithmetic, this becomes 15 by 13%, 22 is 195%, 22 is 19. Notice how we never need to handle the full value of 13s or 2,197. The real elegance of this method becomes apparent as we move to higher powers. Let's examine 13(4). Instead of calculating 13 is 13 times 13 is 13, we can compute it as 13 in 2 is this 13 2% 22. Since we already know 13 2% 22 equals 15, this becomes 15% 22, so 225% 22 equals 5. This pattern continues beautifully. For 13 then 5, we calculate 13 is 4, 13, 1%, 22, 5, 13%, 22, or 65%, 20, 21, for 13, 6, it's 4x, 13, 2%, 22 equals 5x, 15%, 22 equals 75%, 22, 9. Here's a thought-provoking question to consider. How does the choice of decomposition for each power affect the efficiency of our calculations? For instance, why might we choose to calculate 13(7) as 13 to 13 times 1, rather than some other combination of smaller powers? To explore this question, let's analyze the mathematical strategy at work. Each decomposition is chosen to minimize both the number of multiplications needed and the size of intermediate results. When we calculate 13(7), we use the largest previously calculated power, 13(4), and combine it with smaller powers we've already computed, 13(2) and 13(1), performing the modular operation at each step to keep our numbers manageable. This efficiency becomes crystal clear in our final calculation of 13(8). Instead of dealing with an enormous number like 815,730,721, we simply compute 13(4) is 13(4%), 22 x 5x5%, 22 is 25%, 22 is 3. Throughout this entire process, we never had to handle any number larger than 3 digits. The brilliance of this technique lies in its scalability. While our example uses relatively small numbers, base 13, modulo 22, the same principles apply to the much larger numbers used in cryptography. By keeping our intermediate results small through regular application of the modulo operation, we can efficiently compute powers that would be completely impractical using direct multiplication. This efficient computation method serves as a crucial stepping stone toward understanding Shor's algorithm. While we're currently working with real numbers, the algorithm will eventually incorporate complex numbers to find the period of these sequences more efficiently. The ability to quickly compute modular exponentiation through repeated squaring creates the foundation upon which quantum period finding can be built. The transition from real to complex numbers in the next phase of Shor's algorithm represents a fascinating leap in mathematical sophistication. While our current calculations give us a sequence of real numbers, the introduction of complex numbers will provide powerful new tools for analyzing the patterns within these sequences, ultimately leading to efficient period finding on quantum computers. We're exploring complex numbers, a fundamental mathematical concept that powers one of quantum computing's most revolutionary tools, the quantum Fourier transform, QFT. Let's dive deep into understanding how these numbers work and why they're crucial for Shor's algorithm. First, let's address a historical misconception. When Girolamo Cardano introduced these numbers in 1545, he called them imaginary, perhaps an unfortunate name choice that has led to unnecessary suspicion. As our source notes, if we had called them super numbers instead, people might be more receptive to their very real applications in science and technology. Looking at our visual representation, we can see how complex numbers exist in a two-dimensional plane. Unlike regular numbers that only move left and right on a number line, complex numbers can move both horizontally and vertically. This additional dimension of movement gives them powerful mathematical properties that make them essential for quantum computations. Let's examine the specific complex number shown in our figure, 3 plus 2i. We can break this down into two distinct components. The real part, 3 units along the horizontal axis, the imaginary part, 2i units up the vertical axis. The figure shows this as a point plotted at coordinates 3 theta 2i with a vector drawn from the origin to this point. The dashed lines help us visualize how this number combines both real and imaginary components. Here's a thought-provoking question to consider. Why might the two-dimensional nature of complex numbers make them particularly suitable for quantum computations in Shor's algorithm? How does their ability to represent both real and imaginary components parallel the quantum states we need to manipulate? To explore this question, let's think about the relationship between complex numbers and the QFT. The QFT uses complex numbers to perform what our source calls its magic, finding the period of a sequence that will ultimately help decrypt messages. This isn't arbitrary. The two-dimensional nature of complex numbers provides mathematical tools that simply aren't available when working with real numbers alone. Consider how this works in practice. When we need to find patterns in sequences for Shor's algorithm, complex numbers allow us to represent and manipulate quantum states in ways that would be impossible with just real numbers, the imaginary component, rather than being some abstract mathematical curiosity, becomes a crucial tool for encoding and processing quantum information. This is why scientists rely on complex numbers constantly, despite their relative absence from everyday calculations. In quantum computing, they're not just useful, they're essential. The QFT leverages the unique properties of complex numbers to perform calculations that would be virtually impossible using only real numbers. The fact that these numbers don't arise naturally in day-to-day situations has no bearing on their mathematical power. Just as a quantum computer operates in realms beyond our everyday experience, complex numbers operate in mathematical dimensions beyond simple real numbers. This additional mathematical dimension provides exactly the tools we need for sophisticated quantum operations. Understanding these numbers and their graphical representation is crucial for grasping how the QFT works within Shor's algorithm. The combination of real and imaginary components, represented so clearly in our figure, provides the mathematical framework necessary for the quantum calculations that make period finding and ultimately decryption possible. We're exploring one of the fundamental operations in complex arithmetic, the addition of complex numbers. Let's examine how this operation works through a detailed analysis of a specific example that demonstrates the elegant simplicity of complex addition. Looking at our equation, we have two complex numbers, 3 plus 2i and 7 plus 9i. The process of adding these numbers follows a beautifully straightforward principle. We treat the real and imaginary components as separate but parallel operations, much like keeping track of dollars and cents when adding money. Let's break this addition down into its constituent steps. First, we identify the real parts of our numbers. In the first number, we have 3. In the second number, we have 7. These real components are added together. 3 plus 7 equals 10. Next, we handle the imaginary parts. The first number contains 2i. The second number contains 9e. These imaginary components are added. 2i plus 9e equals 11i. Finally, we combine our results to form the complete sum, 10 plus 11i. The process is remarkably similar to adding vectors component by component, which highlights an important connection between complex numbers and geometric operations. Here's a thought-provoking question to consider. Why might mathematicians have chosen to handle complex number addition in this component-wise manner rather than developing a different system? How does this approach mirror or differ from other mathematical operations we perform with two-dimensional quantities? To explore this question, let's think about the mathematical elegance of this system. By separating real and imaginary components, we maintain clear algebraic properties that parallel our understanding of real numbers. This separation also preserves the geometric interpretation of complex numbers on the complex plane, where real and imaginary components represent independent dimensions. This method of addition is particularly powerful because it maintains consistency with our fundamental understanding of arithmetic while extending into the complex domain. Just as we can add the x and y coordinates of vectors independently, we can add the real and imaginary parts of complex numbers independently. This parallelism creates a natural bridge between algebraic and geometric interpretations of complex numbers. Understanding this basic operation is crucial because it forms the foundation for more sophisticated manipulations of complex numbers in quantum computing. When we perform operations in the quantum Fourier transform, QFT, we'll be dealing with many complex number additions, and the clarity of this component-wise approach becomes invaluable. The step-by-step nature of complex addition, keeping real and imaginary parts separate throughout the calculation, also helps us avoid errors and maintain precision in our computations. This becomes particularly important when working with the kinds of detailed calculations required in quantum algorithms. We're exploring the fascinating process of multiplying complex numbers, using a detailed example that shows how we transform what seems like a complicated operation into a series of manageable steps. Let's break down the multiplication of 3 plus 2i, 7 plus 9i, with careful attention to each stage of the process. The first key insight in complex multiplication is that we treat it much like multiplying two binomials using the distributive property to multiply each term of the first complex number by each term of the second. Let's follow this process step by step, starting with 3 plus 2i, 7 plus 9i. We perform four distinct multiplications. First term, x. First term, 3 plus 7 equals 21, real number. First term, x. Second term, 3 plus 9i is 27i, imaginary term. Second term, x. First term, 2i x 7 equals 14i, imaginary term. Second term, x. Second term, 2i x 9i equals 18, 2. Requires special handling. Our second line shows these terms all laid out. 3 7 plus 2i 7 plus 3 9i plus 2i 9i. In the third line, we begin collecting terms. 21 plus 14i plus 27i plus 18 over 2. Here's where we see something interesting. The I2 term is written as 1 2 to make explicit what's happening with our imaginary unit. The fourth line shows further simplification. 21 1 plus 41 term I 18. Notice how the I2 term becomes 18 because I82 equals 1. Finally, we arrive at our elegant result, 3 plus 41i, having combined all real terms, 21, 18 equals 3, and collected our imaginary terms, 41i. Here's a thought-provoking question to consider. Why does the multiplication of complex numbers maintain closure? That is, why does multiplying two complex numbers always give us another complex number in the form a plus bi? How does this relate to the fundamental property that I2 equals 1? To explore this question, let's analyze the structural patterns in our multiplication. When we multiply two complex numbers, we might initially worry that we're creating some new kind of number with I2 terms. However, the property that I2 equals 1 ensures that our result always collapses back into the standard form of a complex number, a plus bi. This process beautifully demonstrates how complex multiplication preserves the structure of complex numbers while potentially yielding surprising results. Note how our original numbers, 3 plus 2i and 7 plus 9i, transform through multiplication into a completely different complex number 3 plus 4 to 1i. Yet this result maintains the same fundamental form of a real part plus an imaginary part. The systematic nature of this process, distributing terms, collecting like parts, and handling I2, gives us a reliable method for performing these calculations, no matter how complicated our initial numbers might be. This algorithmic approach becomes particularly important when we implement complex arithmetic in quantum computing applications, where precise manipulation of complex numbers is essential for algorithms like the quantum Fourier transform. Understanding this multiplication process is crucial because it forms the foundation for more advanced operations with complex numbers in quantum computing. The ability to multiply complex numbers accurately and efficiently becomes essential when working with quantum states and transformations. We're exploring a crucial concept in quantum computing, the absolute value of complex numbers and its profound implications for qubit measurements. This concept bridges classical mathematics with quantum mechanics in a fascinating way. Looking at our figure, we see a complex number 3 plus 2i plotted on the complex plane. The diagram brilliantly illustrates how the absolute value of a complex number is actually a geometric concept. It's the direct distance from the origin, 0 was 0i, to our complex number point. Let's analyze the diagram in detail. We have the real component, T units, extending along the horizontal axis, the imaginary component, 2i units, extending up the vertical axis, a line segment connecting the origin to our point, marked with 13 right angle markers showing we're dealing with a right triangle. The equation at the bottom of our figure shows the mathematical formalization of what we're seeing. Cos 3 plus 2i equals 32, 22 equals 13. This isn't just a random formula, it's a direct application of the Pythagorean theorem to our complex number visualization. What makes this particularly fascinating is its application to quantum computing. In quantum mechanics, when measuring a qubit, the probability of getting either a 0 or 1 depends on the square of these absolute values, ups 2. This is fundamentally different from working with real numbers, where squaring a number and squaring its absolute value give the same result. Here's a thought-provoking question to consider. Why does quantum mechanics use the square of the absolute value ups 2 rather than just the absolute value itself for probability calculations? How does this geometric interpretation of complex number magnitude relate to the physical reality of quantum measurements? To explore this question, let's think about the mathematical structure we're dealing with. The absolute value gives us a non-negative real number representing distance in the complex plane. When we square this value for quantum probability calculations, we're ensuring several important properties. All probabilities are positive. You can't have a negative probability. The probabilities are properly normalized. They sum to 1. The geometric relationships in the complex plane are preserved in our probability calculations. This geometric interpretation becomes particularly powerful when we consider that our diagram shows how any complex number can be understood as creating a right triangle with its real and imaginary components. The absolute value is always the hypotenuse of this triangle, giving us a concrete way to understand the magnitude of complex numbers that we'll be using in quantum calculations. The bracketed portions of our figure highlighting the real part, 3, and magnitude 2, serve to emphasize how these components contribute to the overall structure of the complex number. This isn't just abstract mathematics, it's a visualization of the fundamental way we calculate probabilities in quantum systems. Understanding this relationship between geometry and complex numbers is crucial for quantum computing because it helps us interpret what's happening when we perform measurements on quantum systems. The absolute value squared of quantum amplitudes tells us the probability of measuring particular quantum states, and this geometric interpretation helps us understand why these probabilities behave the way they do. As we move forward in quantum computing, This understanding of complex number magnitudes becomes increasingly important. The quantum Fourier transform, which is essential for Shor's algorithm, manipulates these complex numbers and their magnitudes in sophisticated ways to extract periodic patterns from quantum states. We're examining a fundamental principle in quantum computing, the verification of a valid quantum state vector through probability calculations. Let's analyze this sophisticated mathematical proof that demonstrates why our given vector represents a legitimate qubit state. We begin with a complex valued vector containing two components. First component 1/2 has I23, second component 1/2 plus I6. To verify this represents a valid qubit state, we must prove that the sum of the squared magnitudes equals exactly 1. This is a fundamental requirement in quantum mechanics, ensuring that probabilities are properly conserved. Let's break down this calculation with meticulous attention to detail. First, we calculate the squared magnitude of each component separately. For a complex number in the form a plus bi, its squared magnitude is a2 plus b2. This gives us, for the first component, 1 tandau I23, real part squared, 1 plus g2, imaginary part squared, g123, 2. These combine to give us 1 quad plus 1 12. For the second component, 1 tau p plus I pagi 6. Real part squared, 1 chance tau 2 imaginary part squared, 1 on 6 is 2. These combine to give us 1 half bar plus 1 6. Here's a thought-provoking question to consider. Why is it crucial that these probabilities sum exactly to 1? And what would it mean physically if they sum to any other value? How does this mathematical constraint relate to the physical reality of quantum measurements? To explore this question, let's analyze the mathematical structure in detail. The final step of our calculation shows 1 quad plus 1 12 plus 1 plus 116 1. This isn't just mathematical coincidence. It's a fundamental requirement for quantum mechanics. Each term in this sum represents a probability contribution from different components of our quantum state. The fact that they sum to exactly 1 ensures that when we measure this qubit, we will definitely get one of the possible outcomes, no more, no less. Looking at the individual fractions, 1/4 comes from the real part of the first component. 1/12 comes from the imaginary part of the first component. Half comes from the real part of the second component. 1/6 comes from the imaginary part of the second component. The precision required in these calculations is remarkable. Every term must be exactly right for the sum to equal 1, which is what makes this vector a valid quantum state. This mathematical property ensures that our quantum system behaves in a physically meaningful way, preserving the probabilistic interpretation of quantum mechanics. This verification process is crucial in quantum computing because it ensures that our quantum operations remain valid throughout any computation. Every transformation we apply to this state must preserve this property. This is why we use unitary matrices for quantum operations, which we'll explore next. Today, we're exploring complex conjugates, a fundamental concept that becomes crucial when we extend our understanding of unitary matrices into the complex domain. Let's analyze this concept through both its mathematical definition and its elegant geometric interpretation. Looking at our figure, we see a beautiful visualization of complex conjugates in the complex plane. 2 points are plotted, 3 plot 2i and 3 shift 2i. These points demonstrate a perfect reflection across the real axis, illustrating a key property of complex conjugates. Let's break down what we're seeing in precise detail. The point 3 plus 2i is located 3 units along the real axis, positive direction, 2 units up the imaginary axis, its complex conjugate, 3 2i, is located. The same 3 units along the real axis, 2 units down the imaginary axis. This reflection property isn't just visually appealing, it's mathematically significant. When we denote a complex conjugate with an asterisk, as in 3 plus 2i, we're performing this reflection operation. The real part remains unchanged, while the imaginary part changes sign. The figure also shows us how this relates to the general case. For any complex number of the form a plus bi, its conjugate will be a by. This relationship creates a kind of mathematical symmetry that becomes essential when we work with unitary matrices in quantum computing. Here's a thought-provoking question to consider. Why might the reflection property of complex conjugates be particularly important in quantum computing? How does this symmetry relate to the requirement that quantum operations must be reversible? To explore this question, let's think about the context where these conjugates appear. We're told that unitary matrices are crucial because they can be implemented in quantum circuits. In the real number domain, we could define unitary matrices simply using transposers. However, when we move into the complex domain, we need conjugates to maintain the proper mathematical properties. This connection between complex conjugates and unitary matrices isn't arbitrary. The reflection property we see in our figure, where conjugate pairs are mirror images across the real axis, helps ensure that quantum operations preserve important physical properties like probability conservation and reversibility. Understanding complex conjugates is crucial because they help us extend our mathematical framework from real numbers into the complex domain while maintaining the properties we need for quantum computation. Just as a physical mirror reflects light while preserving its essential properties, complex conjugation reflects numbers across the real axis while preserving crucial mathematical relationships. The simple notation using an asterisk, as in 3 plus 2i, 3, 2i, belies the deep mathematical significance of this operation. This notation will become particularly important as we develop our understanding of unitary matrices and their role in quantum circuits.